All right, this is the DIY operational amplifier built by Philip Segraves and Nicholas Margavio. So we did a lot of explaining about this in the lab report. Um, as you know, it was constructed based on the schematic right here, where it comprises a differential amplifier, current source, another current source, compensation, and push-pull output stage. This overall took quite a bit of time uh, to get to work. There's been a couple of transistors that have been blown, namely these guys, because figuring out the polarity or the direction that they're supposed to face has been an issue. But once we switched to the more standard kind that have a flat edge, it became a lot easier to differentiate what the collector and emitter is. But yeah, with these, you have to look at the notch. But anyways, we have current source right there with that transistor, which connects to those two diodes, which we haven't spent a lot of time in class studying. Normally, the most common current source that you see is comprised of two transistors facing each other, but this one works by just adding the voltage drop that you experience with the diodes, to kind of work in that way. But yeah, we have the differential amplifier, which is these two transistors right there. And then, let's see, we have, the other current source also with these two diodes and transistor, and then the push-pull. I don't know if you can see, but those transistors right there. And then these capacitors were actually added, or no, not added. They're put in series to equal the 22 picofarad requirement right there. I think this added up to like 23 and a half, and that's pretty much the closest I could get with the spacing and the options that I had. But yeah, we constructed a non-inverting op-amp design using two 1K ohm resistors just to add, resistors. And as we know, the formula is 1 plus RF over RN. So, whenever the resistors are equal, that amounts to 1. So 1 plus 1 is 2. And, we saw that right here, where the input signal is the smaller signal and the output is a larger one. And, as you can see, there's a non-inverting property to it, as well as the fact that its amplitude pretty much doubles. So, yeah, like I said, this took a very long time to get to work, but pretty happy with the results that we got. It follows, the characteristic behavior of an op-amp. Yeah, that's pretty much it. This is a physical demonstration, and I know Nicholas Margavio has a simulation demonstration. So yeah, this is this part, and I hope you enjoy.
All right. So this is our transistor operational amplifier circuit. We're trying to emulate the 741 op amp by using transistors and resistors. And so here is the original model that we're trying to create. And so here we have the current source in the bottom left, the differential amplifier in the top left with the positive and negative inputs. This middle section is the gain stage, and then this right section out here is the output stage. And so in Simulink, it looks like this. And so what we've done is we have created a non-inverting amplifier where we have a feedback resistor coming from the output into the plus position. So here is, or sorry, the minus. So this is our circuit that we're going to be emulating. So we have a feedback resistor coming into the plus, and then a input resistance coming into the plus as well, being grounded. And so, and then we're feeding in an input voltage into the negative of 1 volt and 1 kilohertz. And so our values are 1K for the feedback and 1K for the input. So our gain should be 2. And so when we run the circuit, we should get an output of around 2 volts amplitude. So there we go. It shifted a little bit up. This could just be due to the difference in speed between the PNP and the NPN transistors. But all in all, the circuit works as expected with a gain of 2. And we have successfully created an operational amplifier, non-inverter amplifier circuit using transistors and resistors instead of a 741.